All right. Hello. Oh, I need a mic. A little bit. You don't think we need a mic? No mic it is. All right. Hello. My name is Legault. I'm an upcoming junior mechanical engineering student at Tennessee Tech, and I'm going to go over my research project this summer. I was under Alexei's soft matter research, specifically in the battery storage section under Ivan Popov, and this is my summer research project. It is enhancing efficiency in Brillouin light scattering techniques, automating spectral data processing for battery research. So before I go ahead into what I did, I'm going to get some context to make sure we're all on the same page about what the current battery scene is looking like. So currently, it is very hard to make a battery that is safe and easy to process, is safe for the consumer, and has good performance. As you can see here, we have some batteries that are good at kind of two, but it's really hard to make one that's good at all three. So my summer project was more looking towards the performance side of a battery. There's a lot of ways you can do that, but one of those ways is analyzing the chemicals themselves and predicting how the battery will behave. One of the ways you can do that is something called spectroscopy. So spectroscopy is where you take light, you hit the material, and then it can do a lot of different things at certain frequencies, and that can tell you certain things about the material. Specifically, I'm going to be looking at scattering spectroscopy. So what is scattering spectroscopy? There's a lot of different things on the spectrum. However, specifically around the gigahertz range, it's something called Brillouin. And Brillouin can tell you a lot of things, but specifically it tells you a lot of properties about how ions transport ionic liquids. Obviously, that is for batteries. The three main components it can tell you, one is shear modulus. Shear modulus is the resistance for the material to resist like a shearing motion or like a rubbing motion. The second is something called bulk modulus, which is the resistance to squish in three-dimensional space. And the third and most important for the day is rotational molecular relaxation time. That's what we are going to be focusing on today. So to actually get this whole Brillouin light scattering to work is a big logistical nightmare because you first have to clean up the laser, focus the laser, then you have to hit the sample, then you have to contain the scattering, and then you have to do more filtering, polarizing, and then you have to do more filtering, and then you can finally actually do some acquisition. This also has to be completely in three-dimensional space. For some context of how complicated this is, I actually made a manual to help fellow future interns on this whole process. And it's about a 20-page manual to actually fully get this thing set up. So it's quite a big process. So once this is all fully prepared, we can start actually the acquisition and the data curation. So the actual equation we'll be looking for is something called the average susceptibility. It's this very scary equation. Don't worry about it. All it allows us to do is actually fold the equation on itself. And I'll explain that later. But first off, when you see the full spectrum, there's a lot going on, but it tells you all three of the main properties. First, you can see the peaks for the bulk and shear. So I'm actually going to intentionally suppress those. We suppress that in the data treatment process. And now you can see the relaxation peak. However, as well, that big orange peak in the middle, that's just used for calibration. We don't need, so actually I'm going to suppress that as well. And so once we have just the two curves, it also allows me to fold it on itself. So we have twice the data given the same amount of time. Also, the F is just used to filter out the noise in the room. And then A, by the way, I forgot to explain that as well, is actually the variable that allows us to suppress the bulk and shear modulus. So once we have this all properly prepared, this is what the actual spectrum will look like once properly treated. These different colors represent the different mirror distances, which is used during the actual acquisition process itself. But the black line is when I just did some normalizing of the function using a Cole-Davison function. To get here is the data treatment is also a very lengthy process because as you can see, it's actually arbitrary, the units, because we're just looking for the peak. The actual intensities themselves don't matter to us in this current site, in this experiment. We're just looking for where the peak happens because the actual equation itself is just 1 divided by 2 pi, the frequency max. So all I'm using is a Cole-Davison function to find the peak, but to get there is a big also data-driven problem. It requires 3 separate Excel pages with a bunch of columns and 2 manual variables per table to find the actual peak. And this could take anywhere from 2 to 4 hours, depending on the variance and the sample. So my project this summer was how do we increase the efficiency of BLS? And the way I went about that was designing a program in Python. It's an object-oriented program that uses a lot of sliders and overall a GUI to allow you to manually manipulate the data in a more user-friendly way. So the data treatment is much quicker, also allows you to export. So just breaking this down. So first off, the variables, as I described before, you can actually just slide them using a slider to actually shift the graph. You can also turn off or on the filters depending on the actual sample itself. It describes to you the sample, the different data. There's a total of 8 samples you'll take during the acquisition, and that describes those as well. And at the very bottom right corner, I had some pretty big ambitions for this program, but I did not have enough time. I planned on doing some automation, but I did not get to that. That's more towards the future works section. And then as well, once you have this thing programmed full, when you've done all the proper data treatment, you can also export it into Excel or Origin, depending on your preference. And yeah, so this was my program. It uses packages such as picosecond, pi-side6, and overall, and some numpy here and there, but it allows you to do a lot of helpful functions for data treatment. So this whole program actually was a little quicker than expected. So I needed some motivation. So now that we have BLS in a little quick, we can do BLS in a quicker manner. I actually did a little bit of a side project. And I looked, just hear me out here, we're gonna go on a completely little side tangent, something called optimum formation. So once you have a battery fully created, it's unfortunately has a lot of things that can go wrong. You can have things such as corrosion, cracking, dilution, dendrites, a lot of bad things can go wrong on a battery. And one of the ways you can prevent that is something called optimum formation. It's where you intentionally charge the battery with a very high ampage right before you sell it off. And this actually reduces the effects by a lot. I like to think of it as putting a little piece of armor on a battery before you put it into battle. And this just allows you to reduce a lot of these effects in the long run. So unfortunately though, to find that optimum current to charge the battery is a very lengthy process, as you have to do a lot of, each one of these small boxes is actually an individual test that is 40 hours long, because you pretty much have to manually test what ampage is required for which battery to get it to a stable level, which is the optimum formation. And just to be really clear how long this takes, this graph on the right here took a, took a total of a year to make. So it's a very lengthy process. So my mentor had an idea with a fellow colleague of potentially this optimum formation current is correlated with molecular rotational relaxation time. And so we went ahead and did some correlation. We did a question, is there a correlation between the optimum formation current and rotational molecular relaxation time? And we did some correlational testing. The left side, the optimum formation, was taken from a colleague from Australia, because he already did this with the chemicals here. He gave us the chemicals, and I did my BLS on those to get the relaxation time. Unfortunately, we only got a total of 9 done this summer. Obviously, if you look at this initially, it doesn't seem like much of a trend, but our theory was that as optimum formation decreases, relaxation increases, because the theory behind that was it requires less current to get the material itself to degrade if it takes a very long time to the molecule to stop relaxing. Theory behind that is beyond me, but that was the general idea of the trend. We initially think this trend does support that, but it's only 9, so we can't make any conclusive we can't make conclusions. It's only 9 samples. So in conclusion, we believe there is somewhat of a global trend between optimum formation current and rotational molecular relaxation time, but it is very early on, so no conclusions yet. And then also in terms of my program, I think it was easy to use, allows for other colleagues as well to use it. Also reduces time spent on data treatment, which is very useful as well. In terms of future works, I plan on actually making my program inclusive of the entire spectrum of scattering to allow for even quicker data treatment. And also in terms of automated features, that little bottom right corner there, I actually plan on making that functional, as currently it's just a nice looking blue square. In terms of my acknowledgements, obviously want to thank my mentor, Ivan Popov, and obviously the boss, Alexei Sokolov, for allowing me to join their group. And the SMaRT program, Utori, just an incredible opportunity this summer. And thank you very much.
Any questions?
How do you intend on bringing in the other types of spectroscopy in your further research?
Yeah, so go back. So I did not include a full, that's not clear. So when you look at the full spectrum, that includes the entire, so actually, if I'm explaining, look back here. So BLS, when I show you that final data treatment curve, it just shows you the curve here. But if you were to do a full data treatment of the entire spectrum, it was a very wide curve. So it's kind of hard to show this with hands, but ideally, if I included the full spectrum in my program, it would include, I would pretty much be widening it, and it would just show the other curves as well. That answers your question. So yeah, I would just pretty much be widening it, including data treatment of the other programs from the raw data.
Oh yeah, I'll just show.
Yeah.
So I'm just thinking, like in the theory, would you expect to see multiple peaks or only one?
Yeah, so it depends what you're looking for, obviously. But for example, if we're looking for the relaxation time, sometimes actually, especially Raman, so Raman's on the right side, DLS is on the left side. Raman sometimes actually is higher. And when you do the final curve, it's kind of more wiggly. But yes, sometimes they are higher. But especially for electrolytes and lithium based, which is what I did for we just looked straight at lithium electrolytes. Their peak is within BLE. So that's mainly the only reason, because we didn't look at Raman. But we can do it. There are peaks there, but we just didn't do that for this.
Okay, so if there are two peaks, how do you compare the two? Because you say you don't look at the intensity of that.
Yeah, so the idea is we just make them tangent. The curve is the spectrum is completely tangent with itself. So you just would, even if it's completely arbitrary, you would just add the Raman right here. So sometimes but it has to attach here.
Oh, I see what you're saying.
See what I'm saying? Yeah.
Sorry, when you expand into Raman, would you expect it to basically lose stability as it goes further to the right?
It does lose stability. I don't understand the theory behind that, but yeah, typically it kind of obviously looks opposite of the green, and then it just kind of does this big old jump thing. I don't understand why, but yes, it does lose a lot of its consistent curve.
Yeah, thanks. Is there any physics in the width of the peak?
In terms of the physics of the width of the peak, so this might be better to look at this one. So the whole idea is that the big width of the peak is the relaxation time. As I said, it might be better to look right here. So the whole idea is that this is how long it takes the molecules to stop rotating. So the more liquid the material is, or less viscous it is, the wider and taller the peak is. But if you look at a solid, for example, a solid's very static. So those materials don't spin very much. So the more solid and static material is, the flatter this curve is. So if you were to look at you can do this with solid materials as long as they're transparent, because logistically speaking, it has to pass through the sampling. But as long as it's a solid transparent sample, there will mainly just be bulk shear, because that's what's in the sample. But yes.
Yeah, very nice. So it's a damping.
Yes.
Great.